Hello. What I'm going to do is just walk through sections 8.3 and 8.5, which are talking about logarithmic functions, and then we're going to kind of go through some properties of logs as well. So the first things we'll go through are just converting back and forth between exponential and logarithmic form, and then evaluate logarithms without a calculator, which is really similar to what we had done previously with just evaluating different powers and having just kind of a chart of perfect roots. So that chart really helps kind of just ingrain perfect roots into your mind and kind of helps out with this stuff. We're going to go through what it looks like to graph a transformation of a logarithmic function. Again, very, very similar to exponential ones. And then go through some properties. So this was like back when we did exponential properties. So like if I said, hey, I have x to the third times x to the fifth, we knew that we could add the powers together. So similar kind of rules here where we're going to have like a plus and it's going to turn to a multiplication. So we'll go through those. And then at the end, we'll just practice taking those problems and combining logs into one log. So again, it's a lot of the same stuff we've done with exponential equations. Logarithms, by definition, are just the inverse of an exponential function. So the problems themselves are very similar. So first off, rewriting an exponential form or an exponential equation into logarithmic form. So I'm going to take a couple just facts. So 3 to the 5th power is 243, and we're going to rewrite this in what we call log form. So the way you do that is you say I have log, and you say base 3, since 3 is the base number, of 243, and you say that is 5. So I would read that as log base 3 of 243 is 5. And again, that's just another way of writing something from exponential form into this inverse way, which is logarithmic form. This one, again, you can apply the same logic. So I would say log base 4, since 4 is the base number, of 64, and then is 3. So that exponent always going on the other side of the equal sign. Again, just saying 4 to the third is 64. So I'm going to take that same type of logic and just flip it. So now we'll go from logarithmic form into exponential form. So this first one, since 4 is the base, I say 4, and then to the power of 5 is 1024. All right, easy enough. With this one, I would just keep the base as 1/2. To the power of -5 is 32. And just to take that last one just a step further, the fact that I have a negative exponent, just keep in mind something that we could do if I wanted to make the exponent positive. If you flip your fraction on the inside, your exponent becomes positive, and then it's 2 over 1, which is still just 2. And we know that 2 to the 5th is 32. So that's kind of why that works out the way it does, going from a fraction base into a whole number. So we're just going to go through just evaluating some of these, and I'll just show you the way that I work these. I like to just throw an equals x at the end of these, and I usually just write them in exponential form first, so that it says 3 to the power of x equals 81. So when it says evaluate, you're really just determining the value of x, which by rewriting it first, it's kind of just a guess and check. We should know hopefully by now that x equals 4 in this case, and that 3 to the 4th is 81. So all that you do is you just replace this at the end and say is 4. So that's your answer. Same thing here. Again, I could just go to the, just saying 2 to the x power is 128. And then again, just knowing that 2 to the 4th is 16, 2 to the 5th is 32, and then we just get to the point basically that 2 to the 7th is 128. So you can kind of guess and check those in your calculator, although I do believe there is a way of just typing in this left-hand side of the function, and I'll try that towards the end of the video. Next one, we are going from having an integer as a base number, and then all of a sudden there's a fraction for this value. Again, I'll rewrite it first by saying 5 to the x power is 1 over 25. So the fact that I know that I can square 5 to get to 25, but since it's on my denominator, the only way would be to have a negative exponent. So that means that my exponent would be -2. And I know that 5 to the -2nd is the same thing as 1 over 5 to the +2nd, which is 1 over 25. So that's kind of, again, how you would just check and make sure that your answer is what it is. With this one, same type of logic. 2 to the x power equals 1 over 16. I know that 2 to the 4th is 16, so that means 2 to the -4 would give me the 1 over 16. So these last couple are kind of just reversing that, where now my base number is the fraction, and I want to know what power I would have to raise it to get to the whole number, which again, to bring the 8 to my numerator just means I have a negative power. So if I flipped this fraction, it would be 8 over 1. If I flip the fraction, though, my exponent becomes negative. And again, to go from 8 to 64, you're squaring it, so it would be negative 2. And then same thing here, if I rewrote it in exponential form, I would say 1/4 to the x power equals 64. I know that 4 to the third power is 64, so since I want it to be 1 over 4, that means again the 4 would have to come up, exponent would be negative, so that'd be a negative 3. So again, that's just evaluating those without a calculator. So what I want to jump into then is the transformation process, which we knew for exponential functions, we could use anything to the 0 power is 1, anything to the first power is itself, the base number, and we would start off with y equals 0. So that was for exponential form. Since we're going into logarithm land, which is the inverse of that, you can just flip these coordinates. So we're going to use 1, 0, b1, and we're going to have a vertical asymptote instead at x equals 0. So again, this was the exponential form in blue. The red is logarithmic form, and it's going to work exactly the same way. Your base number is that same like base value as we had before. So when I say log base 2 of x plus 2, what I'm saying is the base value is 2. So in this first example, and I'll just switch to green here, I'm still going to start with 1, 0. I'm going to start with 2, 1, and then I'm going to start with the vertical asymptote of x equals 0. So again, I'm getting this 2 from the base number, and then it's going to work the same way it did before, where we go to the argument of the function, which is this part right here, and since it says x plus 2, we're actually going to subtract 2 from our x coordinates. There's no multiplier out front, so if this would have said 3 log base 2, you would want to multiply your y coordinates by 3. So since there's no dilation out front, we're just going to be shifting these vertically up 1 unit. So I'm going to put y plus 1 and then apply these. So I'm going to take my 1 minus 2, which is negative 1. I have 2 minus 2, which is 0. Now since this is a vertical asymptote with an x equals equation, that is going to follow this x minus 2 transformation. So I'm actually going to have a vertical asymptote at x equals negative 2. And then the y values are just going to get 1 added to them. So 0 plus 1 is 1, 1 plus 1 is 2. So from here, we're going to go to the graph. I'm going to find an x value of negative 2. And I'm going to put my vertical asymptote here at x equals negative 2. Plot my points, negative 1, 1, and 0, 2. And then we're going to draw in the logarithmic curve. So you can go in your graphing calculator if you want to see a better visual of this, but it's going to be a curve that's going to kind of, again, look like the inverse of an exponential. So since exponential ones went either like this or exponential ones went like this, the logarithmic ones are going to be a reflection. So keep in mind, again, if an exponential curve looks like this, logarithmic is going to be a reflection over the line y equals x, and that results in a graph that's going to look like this. So that's where I'm getting this shape from, is again, you're going to end up just tapering off here because these values are going to get extremely large x values and very little y values. But the transformation process is essentially the same. And then we move on to these properties. So like I said, it's like when we did exponential problems, we had a batch of properties that we dealt with, the product ones and the quotient ones, power to a power. So the ones here say, okay, if you have the same base value in both of these, and I have two expressions separated by a plus sign, I can condense them to a single log, but then my operation is multiplication. So it's very similar to when I had multiplication before and we would add our exponents. So again, think about those similarities and differences since these are inverses of each other. With this one, I have a subtraction in the middle, which means it's going to turn into a quotient of the two values. And then lastly, I have a power raised to a power, which this c value can really just drop to the beginning of the function and become a coefficient. Alright, so the problems that we're going to have with these are going to really just involve condensing them into a single log. Although I really could go backwards. I could give you a really big log expression and we could break it apart. Either way, at the end of the day, we use these properties when we're solving log equations. So eventually, so not in this lesson, but eventually I'll throw an equal sign on the other side of the equation and put something here. And before you start solving, what you're going to do is condense this down to a single log, and then you'll start working backwards. So you're going to need these skills in the future. First thing is this property that says, hey, I can take a number that's out front and just bring it up to an exponent. So I'm going to do that first, and that's usually how I do these problems, is I break them up step by step. So I can bring my 2 up here, bring over the rest of the problem. So then I see that I have a minus sign here. Again, same base number. So all that you do to write it as a single log is you write the x squared on the numerator and you drop the 5 to the denominator. What you could also see sometimes is this expression written in parentheses, although realistically it does not matter if you kind of space it out right. But that is it. You are just writing as a single log, and that's 2 of the properties that I just used. So same thing with this next one. The first thing I'm going to do is write it as log base 4 of x plus 3, plus log base 4 of 2 to the third. So I'm going to bring the 3 up as an exponent. I'm going to simplify that expression. So if you can simplify it, do it. 2 to the third is 2 times 2 times 2. So this is going to turn into 8. And then I can apply that last property that says, all right, if this is an addition, what I can really do is rewrite this as log base 4 of x times 8, which is 8x. So again, you could throw it in parentheses, and that is it. That is a single log. Next one, I have 3 different expressions. So with this one, I'm going to always start with that first property. If I see a coefficient, I'm going to throw it up top. So I'm going to rewrite this first expression as log base 5 of 4 to the 1/2 power plus log base 5 of 6 minus log base 5 of x plus 1. Next step, I'm going to rewrite this as log base 5. 4 to the 1/2 is really the square root of 4. Plus log base 5 of 6 minus log base 5 of x plus 1. You do not by any means have to do every step of this, just since this is a video of me showing you how to do it, kind of breaking it up step by step. But right away, if you just realize that I'm going to be taking the square root of 4, you can go right to the step of just saying that this is going to end up being 2. So you can show as much work as you need to. Again, I usually break this up by doing the exponent part first and then evaluating from there. But it gets to this point where at the very end I realize that I've got this addition between the 2 of them. So I'm going to take care of that right away between these first 2. So reading this left to right, I would say log base 5 of 2 times the 6, which is 12, and then minus log base 5 of x plus 1. So then your last step is just acknowledging that this is a minus, so that means I'm going to be dividing these 2 parts. Again, they have the same base. If they did not have the same base, you would not be able to combine these 2 expressions. And this is what you end up with. So again, it condenses that ginormous logarithm into 1. And then the last problem. So I'm going to first rewrite this, again with the negative 3 up top as a power. So log base 2 of, and that is x to the negative 3rd, plus log base 6 of 6. I'm going to rewrite this as log base 2 and then simplify this as 1 over x to the positive 3rd plus log base 6 of 6. Now, as you know me, I like to make typos all the time. I totally do that intentionally. So like this typo that I have here, this was supposed to be a 2 so that I could condense these into a single log. But as it works out, I cannot combine these because I don't have the base numbers. So since my bases are different, I cannot go any further than this. So yeah, my typo kind of made up for that. So we cannot go any further, so I'm going to stop the problem there, and that is it. Now I'm going to bring in the calculator, and I just want to see if this works real quick. If I hit alpha and window, that's it. Okay, so on the newer operating systems, if you hit alpha and window, I wanted to go back to these first problems. If I hit log base, so if you have this option on your calculator, you can go back to this, but these were the ones where you could just type in a base value and the value that comes after it in the parentheses. Now this again, just to show you, this is saying 2 to what power is 16? So before I hit enter, just kind of brainstorm real quick what that answer is. And it's going to be 4. 2 to the 4th power is 16. But again, if you have the newer operating system, you can check your answer that way.